Hey everybody, welcome to a brief introduction to C. In the next 20 to 25 minutes, I'll go through the history of the C language, we'll discuss some of the features that make C a great language, and we'll dig deeper into the standout features of C. We'll then do a code demo where I'll be solving one of the exercises on the C track, and then we'll finish off with some learning resources that you can use to learn C. I'm excited, so let's get started. C was developed by Dennis Ritchie at Bell Labs in 1972. It was originally intended as a systems programming language to help them write small utilities for the Unix operating system. They ended up liking it so much that they rewrote the Unix kernel in C, and it was a success story ever since. C is a compiled and statically typed language, and it supports the imperative paradigm. So when you write C code, you're writing imperative code. As I mentioned, C is quite an old language. It's actually one of the oldest programming language there is, and it has been used for tons of different things. Like I mentioned, Unix, but also Linux has been written in C. Git has been written in C. Many of your device drivers will have been written in C. It is wildly successful, and there is so much C code out there. It's incredible. C has also been influential in other ways, where it is at the root of what we call the C-like family tree of languages. So if you're talking about a C# or a Java, they are part of the C family tree. And that's because they share a lot of their characteristics with C. So C is the grandfather of these languages. C is also a standardized language. So you have ANSI C and ISO C. So it's an official standard with a specification on what should be in the language and what the semantics are. And that standard is still, even 50 years later, still being revised and updated. So it's not a stagnant language at all, even though it is by the relative standards ancient. Let's go into some of the reasons why C is a great language. First of all, it is a fairly small language. And with small, I mean that there are relatively few syntactic constructs in the language. This means that if you want to learn the various things that are in the language, it's not that hard actually, because there are relatively few of those concepts. And that makes learning or mastering the language easier. It's also a very lightweight language. And with lightweight, I mean memory and CPU usage are often very low compared to maybe other languages. And this is particularly great for resource-constrained environments. So if you have a bit of hardware or you have an embedded system, these are resource-constrained environments, and you have to usually eke out every bit of performance or memory. And C is great for that because it has so little overhead. And that's also one of the reasons why you find C at such a wide variety of places. C also is great because it has a ginormous amount of libraries already written in C for you to use. C code is everywhere, C libraries are everywhere, and almost everything that you can think of has been written in C and is thus available for you to use in C. And finally, C also interfaces well with hardware. Not only, as I mentioned, is it integrating well with resource-constrained environments, but it also has a fairly direct mapping to underlying hardware mechanisms. So if you write C code and you need to interface with hardware, it's a fairly optimal way in which you can do that. There is little overhead, and it feels quite natural in C to do that. Let's discuss the standout features of C. The first feature is that C is great for writing high-performance code. There are a lot of characteristics of the language that make it great for writing highly performant code, such as features like pointer arithmetic and being able to write inline assembly. But in a more general sense, the way that C is designed is such that it maps very well to the underlying hardware, so the CPU. And this gives you a lot of options to optimize your code. And this results in C being used for example, supercomputers and tons of other places where performance is highly critical. The second standout feature of C is its manual memory management. If you're used to more modern languages, you're probably not used to thinking about memory management in the way that you need to do it in C. With a modern language, you allocate objects and you don't bother with how that is allocated or how much memory that needs, and you definitely not bother with deallocating things when they're not needed. With C, though, you as the programmer have to take care of that by yourself. So you have to decide, how big is this piece of memory that I need to allocate? When do I need to deallocate it in order to not have memory leaks? And while this can seem like a chore, it's actually a great feature of C too, because it gives you a lot of power. You just allocate when you need it, and you can free things when they're not needed. With those modern languages, they often rely on a garbage collector. And that will mean that at some undetermined moment, the garbage collector will look at things in memory and then try to figure out what is not needed anymore. And it can trigger garbage collection pauses because it needs to be static. But with C, you have none of that. You are responsible for the memory, but that gives you very predictable characteristics. So you know when things are deallocated, and you can tweak and optimize things for that. So that's actually a great boon for memory usage and performance. The third and final standout feature is that C code basically runs anywhere. It is very hard to find a platform where C doesn't run. And there's a couple of reasons for this. First of all, C has been around for a long time, over 50 years. So many people have taken the opportunity to write support for their platforms in a C compiler. Secondly, the C language is very good to run in constrained environments. So if you are developing a new platform, it often makes sense to start adding support for a C compiler to run things on, because it's fairly natural, and you can build on all the wide variety of other platforms that have already had support for C added to them. You can also see that this runs anywhere is a feature of C that's still being appreciated in the fact that some languages actually compile to C instead of machine code. So what they do, they take their own source code, transform it into C code, and then use one of the available C compilers to actually compile to machine code. And what this gives them is that they can now basically target any platform that C can run on, which means basically any platform. And you can still see that even with newer languages, there is still a reliance on C, and C is still highly influential. Let's look at some actual C code. I will be solving the Hamming exercise on the C track, and the Hamming exercise is one where you take a string and you return the number of positions where they have different letters. So these are DNA strings, and you see the letters C, A, G, and T. And what we need to return is the number of positions where they have different letters. So in this case, there are 7 different occurrences where they have different letters at the same position. So we return a Hamming distance of 7. And that is what we will be implementing. Before we start coding, I'd like to mention that I'm using Visual Studio Code as my code editor. And I have installed the C++ extension developed by Microsoft to give me a bit of IntelliSense and a bit of syntax highlighting. And I highly recommend you trying out this extension to see if you like it. So let's get into some actual code. Let's look at our starting point, Hamming.c. Hamming.c contains just a single line of code, which is #include Hamming.h. And without going into too much detail, header files are definition files where you specify types and functions that you'd like others to use. So if we control click on Hamming.h, we get to its implementation. Forget about the bit of boilerplatey things. We are mostly interested in this line of code, which is a function definition. It is only a definition, as you can see. There is no implementation. And that's often the case with header files, where you have a definition, but the actual implementation is done in the Hamming.c file, so in its corresponding source file. In our case, we have a single compute function that returns an integer, and it takes 2 parameters, a left-hand side and a right-hand side, which are our DNA strings. In C, though, you don't have the concept of strings, and instead you have the concept of character arrays, or basically character pointers. So the way that you have to think about it, for example, if you have Hamming, you would have a bit of memory, and then you would have a byte specifying that is an H, an A, etc., etc. And at the end of the string, there will be a special character, \0, which is the null terminating string character. And that is used to figure out when the string ends. Because there is no object of a string that contains a length. You just determine it by having a starting position, which is what the pointer is pointing towards. So a memory location. And then you continue with the subsequent memory locations until you reach the null terminating string, and that's the end of the string. It's very different to how you work with strings in other languages, but we'll see how this works in a minute. To implement our solution, we need to copy this function definition to our Hamming.c file. We'll remove the semicolon and add curly braces. We need to return an integer, so we'll just do return 0. And then let's run our test to see if we get anything passing. So make test. We actually get an error. And this is because we have a function that has defined parameters that we don't use. So we can't even compile this. So let's start using it. The way that I think we should start is to handle the error case. And in Hamming, the error case is where the strings have unequal lengths. And if we look at the test file, we can see that, hey, these two strings have unequal lengths. Then we need to return a -1. And this is very C-like because C doesn't have exceptions. So you can't throw an exception. And there is no result type or anything like that. So by convention, many C functions, in order to indicate an error, they return a special value. And -1 is used quite a bit. So let's try and implement that. So how do we get the lengths of these input strings? Well, we include something that's in the C standard library. So we'll do include, and we'll do string.h. And then we have functions available to us to iterate over a string and to figure out its length. So we have strlen, which is short for string length, left-hand side, and we can use this in an if statement. So if string length of the left-hand side is unequal to the string length of the right-hand side, then we return -1. I'll save this, and hopefully we get some passing tests, and we get everything compiling because we're now using the parameters. And we get indeed 9 tests, 2 failures, 0 ignored. So we can see that a lot of things are not actually passing because, well, they are working with empty strings and they have a distance of 0. Not everything, of course, because we haven't done any actual computation. But the key thing that we now have is that the one where strands are different sizes, that one now works because we have successfully guarded against that. The next step is to compute the distance. So we need to iterate over the strings. So there's a couple of ways in which we can do this. One of them is to define variables for the string length, because we don't want to calculate it twice. So let's do this. And the return type of this is size of t. So in C, you have to explicitly specify the size. So we'll call this left-hand side length equals, and we'll do size t is right-hand side length is this, and then we'll replace our existing calls with these new values. And then we can write a for loop to iterate over the strings. Well, at this point we know that they have equal lengths, so we just need one of these. So we can do int I equals 0, I is less than the length of left-hand side, and we increment I in after each iteration. So, and then within this function, this bit of for loop, we need to compare these two arrays, these two strings. So we need to do something special. So we can do if left-hand side, and then we'll index via I is not equal to right-hand side, and then the I index, then what do? Well, we need to keep track of the distance. So let's define a variable for that. Int distance is 0. One thing to consider is that values are not initialized by default, so always initialize values. So this is one thing. Then we do distance plus plus, so increment it, and at the end we return our distance. And let's see what this gives us. Oops, an error. So we're now doing things that are somewhat differently because it says we can't compare integer expressions of different signedness. So we have int and size t. And size t is actually unsigned. So we could fix this by doing this, by being explicit, and then we have everything passing. We'll fix this in a second, but for now we have a working solution that passes all the tests, but there's a lot here that we can do to clean this up. Let's see how we can change this bit of code using some C features. So one thing that we can do is we can use the fact that if we're doing this little bit of iterating, but you also can do pointer arithmetic. So if you're doing left-hand side plus plus, it's like moving the pointer in memory one place to the right. So that is exactly what we need for the iteration over the characters. So instead of doing this for loop, I'll put it in the comment here, we can do, we don't do any initializer, so we're going to keep this empty. And then we're going to do two things. We're going to say if the left-hand side is, so star left-hand side means if what's in the left-hand side, so the thing that is being pointed to, so the actual letter, is not equal to \0, and the right-hand side's contents are not equal to \0, then what we can do is we can increment the left-hand side and increment the right-hand side. And then within this function, we can, instead of doing indexing, we are already at the right letter because we are basically changing the letter view one at a time. So we're going to do if the contents of the left-hand side are not equal to the contents of what the right-hand side pointer is pointing to, then we increment the distance. So now we have a bit of code that works. So let's just remove this for now. We do need to do something with it in a sec, but let's see what this gives us. And it gives us a lot except for the failures. So the failures are all having to do with the checks at the end. So whether or not the strings are unequal lengths. We'll remove this too. And the way that we can do this is, well, we have the values of left-hand side and right-hand side after the loop is finished. And if they were of unequal lengths, one of them must not be the terminating character. So if the contents of the left-hand side are not the terminating character, or the contents of the right-hand side are not the character, then we return -1. So run this again, and now we have everything passing. So we've changed our string length calls to some pointer magic. So this might be quite tricky if you're not used to doing pointers. And you can basically see pointers as a level of indirection. So this hard pointer is not actually pointing to a character, but to a location in memory that contains a character. And the thing that we're doing here is we're checking if the thing that is at the memory position that we point to, which is the star, so that's its contents. So that is the character. But then with this, we are incrementing the pointer. So we're moving the pointer to the next position. So it's no longer pointing to the H of Hamming, but to the A of Hamming, etc., etc. And then we are looking at its current value, so that's the star again. And in the end, if they were unequal lengths, that means that one of them must not have terminated. So then either one of them is doesn't have the \0 character, and then it must be -1. So that's all fine. We can do a bit of magic still, and we can actually remove this bit, because in C, that's totally fine. In C, there is no requirement for a Boolean condition to actually be a Boolean. And the actual rules are defined mostly, but this is absolutely valid C code. So let's run it. It still works. We can do the same thing here. So here, and we can run it again. And now we have a completely working version. A final thing that we could do is we can use the ternary operator. So we're going to say, if this is true, then we're going to return -1. Otherwise, we'll return the distance. And this still all works. It is very concise. And this is often a feature of C code where pointer arithmetic, so the thing where we are iterating in memory. So we're changing the memory position via integer arithmetic. That gives you a concise way of checking things in code, but it's not always readable. It becomes readable once you get used to this. But if you haven't seen a lot of C code, don't be disappointed that you don't yet fully grasp this. It will take a while to get used to. But you can also see that there are many things that can go wrong with this code. For example, both inputs could actually be null, and we haven't guarded against that. So we could do that still. We could add if not left-hand side, or we could do if left-hand side equals null. They're both valid. Then we'll return -1. So that's absolutely valid. So that should all work because we don't have any null tests. But when you write C code, it is very, very critical to never trust the inputs unless you are passing it yourselves, because this could be null or it could be malicious. There are a lot of things that can go wrong, and there are standards. So there's a search standard on how you should be writing your C code that can help you prevent all these mistakes. So I wonder what they're saying about my code, but this is fairly idiomatic C code, and you have to get used to this quite a bit. But once you get all these pointer semantics in your head, you'll see that these are actually used in other languages too, even though they might be a bit more hidden to you. Let's go over some of the resources that you can use to learn C. First of all, you can learn C on the C track on Exercism. The C track has over 70 exercises, and they have a wide variety of topics and difficulties. So there should be something there for everybody, and I highly recommend you trying it out. A second resource that you can use is the learnc.org website. And that website has a large list of topics, and they will have interactive tutorials where you can be running your code and have these little exercises that you can use, all to learn these concepts of C. And then the third resource that I would like to recommend is Harvard University offers the CS50's Introduction to Computer Science course online for free. And that doesn't only involve C, but it does involve C, and you can learn the basics from it very well. So I highly recommend this course too. And with that, we've come at the end of our video. I hope this video has been useful to you and that you're now keen on trying out writing some C code, or maybe you already know some C, you want to get back into it. If you do, let me know in the comments. I would really appreciate it. And have fun programming in C. See you next time. Bye.